Hello, welcome to this video. Continuing on with the motion of charged particles in electric fields, we'll be looking at electrostatic force and uniform electric fields. The picture that I've included on this one is a 3D example of oppositely charged, well it's 2D obviously, but it's a 3D representation of oppositely charged parallel plates. Often we only see them in that like two rectangles that are like sliced through, but I thought it potentially could be helpful to visualize it in a 3D sense. So this is like actually what is being talked about when we're talking about oppositely charged plates, rather than that just here and we're in two-dimensional land. So yeah. The magnitude of the electric field away from the edges between two oppositely charged parallel plates at a distance of d apart, where a change in V is the potential difference between the plates, is given by the formula electric field strength equals the potential difference divided by the distance. The force on a charged particle moving in a uniform electric field is constant in magnitude and direction, thus, I think that should be thus producing a constant acceleration. In stage 2 physics, sorry, this should be dot pointed and indented, you'll be expected to be able to describe the motion of charged particles parallel or anti-parallel to a uniform electric field. You'll need to be able to solve problems involving the use of this formula here for a magnitude of electric field. You'll also need to be able to derive this formula here for the acceleration of a charged particle in an electric field, and you'll need to be able to solve problems using said equation for the as well as the motion formulae. So think about our kinematic equations, and this is for the movement of charged particles parallel or anti-parallel to a uniform electric field. That seems like a lot, but it's actually hopefully not too bad. It's just a lot of writing to describe what you need to be able to do. So the work done when a charge is moved through a potential difference in an electric field is given by this rule here. So work is equal to force by displacement, or force by the distance from the point where the electrical potential energy is 0. It's also given by charge of the particle multiplied by the potential difference. Given that this is equal to this, we can rearrange this to have force divided by charge and potential difference divided by displacement. Hopefully you can see that I've just rearranged this part here. We know that electric field strength is given by force per unit charge, so the term here can be rewritten just as E, and that's equal to the potential difference divided by, we'll just replace displacement S with D, and that's this equation here. So, as we've just derived, the electric field between two oppositely charged plates is given by this formula here, and the units are in volts per meters because potential difference is measured in volts and distance is measured in meters. So a quick example, we've got two oppositely charged plates that are 4.5 centimeters apart, and they're connected to the positive and negative terminals on on a 9-volt battery. What is the electric field strength between the plates? So as a visual, we've got maybe positive plate here, negative plate here. We're 4.5 centimeters apart, and we're connected to the positive and the negative on a 9-volt battery. So all we need to do is use our equation for electric field strength, which is equal to the potential difference divided by the distance between the two plates. That should be a bit closer down here, apologies. Cool. So our voltage, or our potential difference is 9 volts. So we can just pop that here, and our distance is 4.5 centimeters, which in meters is 0.045. If we pop this into a calculator, then we'll get 200 volts per meter. And that's our strength of the electric field between the two plates. Moving on to electrostatic force on a charged particle or a charge Q. It's constant in magnitude and direction in a uniform electric field. This means that the resulting acceleration of charge Q, of a charge Q, is going to be uniform as well. And it's going to be towards the opposite plate to the charge of Q. So if Q is positively charged, it will be accelerated, or it will accelerate towards the negatively charged plate, and the electrostatic force will be in the direction of the negatively charged plate. If Q is negatively charged, it's going to want to move towards the positively charged plate. So force is given by the strength of the electric field and direction of the electric field multiplied by the charge. From that, we know that F equals ma, so we can just sub that in. So ma equals electric field strength by the charge, and therefore acceleration is going to be equal to electric field strength by charge divided by the mass of the particle, and this is going to be measured in meters per second squared. So as a quick example, we've got a proton that's accelerated through an electric field with a magnitude of 5 megavolts, 5 megavolts per meter. Mega is by 10 to the 6, so that's 5 by 10 to the 6 volts. What is the magnitude of the proton's uniform acceleration in the electric field? So we'll use our acceleration rule, which is A equals electric field magnitude or strength by the charge, and then divided by the mass. On your formula sheet, you'll be given the charge of a proton. You'll also be given the mass of a proton. The charge of a proton is just going to be equal to the charge on an electron, but just opposite. Electrons are negatively charged, protons are positively charged, because they balance each other out. So acceleration is going to be equal to the field strength, which is 5 by 10 to the 6 volts, and then the charge, which is 1.6 by 10 to the negative 19 coulombs, and the mass of the proton is 1.673 by 10 to the negative 24. And then pop it all into your calculator. Sorry, I think it's not 24 actually, I think it's 27. Pop it all into your calculator and you'll get 4.8 by 10 to the 14 meters per second squared. And that's the magnitude of the proton's uniform acceleration in the electric field. So moving on to motion of charges in uniform electric fields, we can use the equations of motion to describe the motion of charges in uniform electric fields, and that's because the acceleration, that is because the acceleration is constant in a uniform electric field. I'm not going to rehash the equations of motion because you've got them on your formula sheet, and hopefully they're at the mid to forefront of your mind, given that we use them for projectile motion. What I am going to touch on is parallel and anti-parallel motion, as mentioned in this point here, which you have to be able to do. Again, sorry, that should be indented and dot pointed. That's one of the expectations of stage 2 physics. So parallel motion is when, so the electric field is going to be from, I'm going to use what colour? I think I'll use orange, from positive to negative. There are our field lines. So in this parallel motion, the direction of the motion of the particle is in the same direction as the electric field. So velocity of the particle here and the field lines are pointing the same way. In anti-parallel motion, the velocity is pointing in the opposite direction to the electric field. So it's still in the same, I guess, orientation in terms of that it's like parallel with the field, but it's not in the same direction as the field, therefore it's anti-parallel. So we've got a proton, it's entering a field midway between two parallel plates, and the parallel plates are 5 centimetres apart. What is the electric field strength if a potential difference is 500 volts? So to find this, we use our electric field strength equation, which is E equals potential difference over the distance between the two plates. So the magnitude of the electric field, or the electric field strength, is going to be 500 volts divided by 5 centimetres, which is 0.05 metres, and that is going to be 10,000 volts per metre. Next question's asking, what is the magnitude of the proton's acceleration? So to work this out, we'll use this equation here. Acceleration equals magnitude of the electric field, or the electric field strength, times by the charge on the proton divided by the mass of the proton. The charge on the proton is 1.6 by 10 to the negative 19 coulombs, which is the corresponds to the charge on an electron. Mass of a proton is equal to 1.673 by 10 to the negative 27. So acceleration is going to be equal to 10,000 by 1.6 by 10 to the negative 19 divided by 1.673 times 10 to the negative 27. Pop it all into your calculator and you'll get an answer of 9.56 by 10 to the 10 to the 11 meters per second squared. So that's the acceleration of the proton. Now I want to know, what is the time taken for the proton to reach the negative plate? And this is where we can use our kinematic equations. So the time taken can be found by using this equation here. So displacement of the charge, and it will be vertical, because if we think back to the picture I had at the start of this video, there could potentially be vertical and horizontal motion, but we just want to focus on the vertical motion here. So, as in because it's 3D, there could be both vertical and horizontal motion. So the displacement of the charge vertically is equal to the initial velocity vertical of that charge, and then multiplied by time, and then plus half acceleration of the charge vertically, and then by time again. The initial velocity in this situation is going to be 0 because it's going to start with no velocity. Therefore, this entire term here can be cancelled out. Then we're left with displacement of the charge vertically is equal to half acceleration of the charge vertically by time. We can rearrange that to get to, sorry, this should be time squared up here, my bad. We can rearrange this to get to time is equal to the square root of 2 by the displacement or distance of the particle divided by the acceleration of the particle. This will be equal to, go back and have a look. So it's entering midway between the two parallel plates. That means that it's going to be entering at 2.5 centimeters. So 2 by 0.025, and then the acceleration we worked out, it was 9.56 by 10 to the 11. Therefore, if you pop it all into your calculator, the time taken is going to be 2.29 by 10 to the negative 7 seconds. So that's how long it's going to take for the proton to reach the negative plate after entering that electric field halfway through, or at a halfway point between the positive and negative plate. Last question for this is we want to find out the vertical component of the velocity of the proton upon reaching the negative plate. So to find that out, we can use the velocity of the charge vertically, and that would be the final velocity is equal to the velocity of the charge vertically initially plus the acceleration of the charge vertically by time. So this is what we're looking for here, the velocity of the charge vertically, the final velocity of the charge vertically. We already worked out that the initial velocity is going to be 0 because it starts off for a moment stationary. So we're just left with the acceleration of the particle, which is 9.56 by 10 to the 11, and the time taken, which is 2.29 by 10 to the negative 7. Pop all this into the calculator, and this will end up being 2.19 by 10 to the 5 meters per second, and that's your final velocity for that proton. The last thing I quickly want to look at is just a conversion. You might be asked at some stage to convert electron volts to joules. So electron volts are used as a unit of measurement to describe the energy absorbed, emitted or stored by atoms, molecules or subatomic particles or photons, and this is because the energy of these particles is very low, so it doesn't make that much sense to use joules for these particles, but every now and then you have to convert between the two. 1 electron volt is equivalent to the work done when an electron is accelerated through a potential difference of 1 volt. So 1 electron volt is equal to 1.6 by 10 to the negative 19 joules. And the reason this is the case is because work is equal to charge by potential difference. If our charge is 1.6 by 10 to the negative 19, and we're going through a potential difference of 1 volt, then our work is going to just be equal to 1.16 by 10 to the negative 19 joules. So that's the level of energy, or the content of energy, that 1 electron volt has. If you're converting from joules to electron volts, you divide by 1.6 times 10 to the negative 19. If you're going from electron volts to joules, you multiply by 1.6 times 10 to the negative 19. So if you're going from joules to electron volts, you're going to have more electron volts than you are joules, so dividing by this tiny number is going to give you a bigger number. Conversely, if you're going from electron volts to joules, you're going to have less joules, so timesing by or multiplying by this tiny number will give you less as a result. So a quick example: particle accelerator accelerates proton beams to an energy of 6.5 by 10 to the 12 electron volts. Calculate the energy in joules. Energy in joules is going to be 6.5 by 10 to the 12, and we're multiplying by 1.6 by 10 to the negative 19 because we're going from electron volts to joules. This is going to be 1.0 by 10 to the negative 6 joules. Next example, state the quantity of energy in electron volts transferred to an electron accelerated through a potential difference of 70,000 volts, or 70 by 10 to the 3 volts. So the way that I'd think about this is if 1 electron through 1 volt is equal to 1 electron volt, then 1 electron through 70,000 volts is going to be 70,000 electron volts. And that is it for this video. Apologies, I think it's a long one.